yet another video on our channel Euclid Mathematics. As we all know, CSIR NET SET and Gate exam is coming. So we have started lecture series on ring theory. Already I have uploaded plenty of the videos on my channel. If you wanted to see more videos or previous year solved question from ring theory, you may check it into my playlist. So plenty of videos are there. So in my today's video, I will explain to you all the definition of a ring theory and how the property of a ring theory we can apply to the examples. So let's get started our today's example. I will explain to you all everything is a group, non-empty group, okay, which having two operation at the same time. So, okay, so here like addition, multiplication, okay, this operation at the same time, okay. So when this operation hold at the same time and some certain property of a group, then we say that it is a ring, okay. Okay, so what is the definition of a ring? R be a non-empty set, okay. We need that a non-empty set. R under addition and a dot, okay, it is a dot represent multiplication, okay, is said to be a ring. So if it is a ring, then it need to satisfy some certain properties, okay. So here are some certain properties here. So with respect to first operation, so first operation it is here as addition. So with respect to addition, that ring need to satisfy commutative property, okay. That means R under addition is a commutative group. When it hold the first property, so we will go for the next property, okay. So commutative property, under its we have to show two elements from the ring. If all A belongs to R, I consider the element from the ring, okay. If A belongs to R and second element B belongs to R, then closure property it says that their addition A plus B also which belongs to R, okay. R means ring here, okay. So if A belongs to R, B belongs to R, their addition it goes to the R, then we say that it's having closure property, okay. Then after of that it need to satisfy second property. It is a associative property. And what associative property? It says that if we have three elements, okay, so associative property we take three elements like ABC from the ring and we are looking for the only addition, okay, the operation under addition for commutative property, okay, commutative group, okay. So for associative we take their addition, first element added to the next two element and first two element added with the third element, okay. So like A plus B plus C which is equal to A plus B plus C, okay. So then we say that it satisfies associative property. Identity element need to be there, okay. So identity from if we take identity from ring such that if we add, we are looking for addition, so we have to add identity to that element like A plus E which is equal to E plus A which is equal to A, and all A which is coming from ring, okay. So then we say that our group which is having identity element, okay. And last one it is the inverse, okay, second last it is the inverse. If A belongs to R, there exists B belongs to R, okay. So if we consider any element from our ring, okay, so we always get there exists one single element for that element A, such that if we add that element to A like A plus B or B plus A, we will get the identity element, okay. So this one is the inverse property. And last one for the commutative group which is a commutative property, okay. That means take the addition for two element and show that A plus B which is equal to B plus A, like A plus B. Instead of that you may select any other variable, okay. I consider here A and B just for the understanding only, okay. So A plus B which is equal to B plus A and both A and B from ring, okay. Then we say that our first property R under addition is a commutative group, okay. And this is not only the property we needed for ring, we have some other property too, okay. Now next property it says that with respect to second operation, so we have here multiplication, okay. With respect to second operation, R ring dot, okay, that dot means multiplication, okay. With respect to second operation, our ring is a semi group, okay. It need to hold the property for a semi group, and the semi group it says that it need to have two properties like a closure and associative. Now here we have operation multiplication, okay. Now what closure property says that take any two elements like A belongs to R, B belongs to R and show that their dot product in R also, okay. So this one is the closure property with respect to multiplication. It is similar like addition, okay. So closure property for multiplication it says that take any two elements from the ring and show their multiplication it is also in a ring, okay. And now let's go for further associative property, okay. So associative property with respect to multiplication it says that A dot under bracket b dot c, which is equal to a dot b dot c. Okay, and all three elements which is coming from the ring. Okay, then if these two property hold, then we say that our multiplication ring under multiplication is a semi group. Okay, so it's need to satisfy commutative group property, second semi group property, and the last one it is here left and right distribution law. Okay, now distributive property need to satisfy also. Okay, so it is here, if we consider a b c from our ring, then we have to show a dot b plus c. Now observe here, we have addition for next two elements, so a dot b plus c can be written as a dot b plus a dot c. Okay, so this one is the first property and this one is the second property. So make the bracket for first two element and add it and multiply to the third element. So a plus b dot c, which is equal to a dot c plus b dot c. So it is the third property here, left and right distribution law. Okay, so to show any order pair like R under addition dot, it is a ring, that we have to show R under addition is a commutative group. Under commutative group we need to show these properties like a closure, associative, identity, inverse, commutative. Okay, and after of that second property R under multiplication, ring under multiplication, it is a semi group. Under semi group we have to show closureness and associative property, and last one left and right distributive law. Okay, so for distributive law we have to show these two properties. Okay, so if all these properties hold, then we say that our given R under addition dot is a ring. Okay, now let's understand some example that can give us clear idea about our definition and about properties. Okay, now here I consider here first example, so show that z under addition dot is a ring. Okay, it is here integer, z I taken z integer with respect to addition and multiplication is a ring. Okay, so we have to show z satisfy all these property above we learned earlier, that z satisfy all these property, and then we show that we have to show that z under addition is a ring. Okay, now let's get start the solution of our example. So if we wanted to show z under addition dot is a ring, then we have to show first property z under addition is a commutative group. Okay, and for commutative group we need to hold next five sub property. So first property it says that closureness. Okay, so if a belongs to R, b belongs to R, then their addition need to be an R. Okay, so you may consider any element from the integer, surely we will get their addition in integer group itself only. Okay, so first property is quite easy to hold for any element. Okay, like if a belongs to R. Now if you wanted to consider any counter example for this, you may consider like a which is equal to 2 which belongs to Z. Okay, integer group. Okay, and b which is equal to 3 which belongs to Z. You may consider any element, and we can easily show that if a belongs to R, b belongs to R, then a plus b like a 2 plus 3 which belongs to Z means ring. Okay, we consider ring as a Z. Okay, so you may consider any counter example. Okay, so it can be easily seen that Z under addition is a close, it is holding closure property very easily. Okay, and that means Z under addition is a cyclic group. As we all know that integer group is a cyclic as well as abelian. Okay, it hold under addition, it hold a plus b which is equal to b plus a. Okay, it is abelian as well as cyclic, then we show that we can say that Z under addition is a commutative group. Okay, so it holds the property for commutative group, all property for commutative group. Okay, so that means all property means we have to show these a plus b belongs to R in a ring, a plus b plus c which is equal to a plus b plus c. Identity element is always there. Okay, identity element under addition is a 0. 0 is the identity element for our integer group. Okay, so if we consider any element plus 0, 0 plus any element, we always get the a. Okay, that element itself. And for inverse of our any element. Okay, so if we want, if we see the inverse element for our integer group, if we consider any element like a, so a plus b which is equal to b plus a which is equal to identity means we want the 0. So if I consider a as a first element as a and b second element b as a minus a. Okay, a first element as a, second element b as a minus a, or minus a plus a, we can easily show that their addition it goes 0. Okay, and exactly 0 is an identity element of our group. Okay, so inverse property it also hold here. And now last one, it is a commutative for under first group, a commutative group. Okay, so a plus b which is equal to b plus a, it always hold. Okay, R dot under multiplication, we have to show Z is a semi group. Okay, for the property of a semi group, we have to consider Z under multiplication. Okay, so take the two properties, closeness and associative here. Take the two elements A from our integer group, B from our integer group, and show that their multiplication it also goes to our integer group. Okay, so this one is the first property, and now let's go for the second property. So second property, it says that take the any three elements and show their multiplication equal for the two different brackets. Okay, so here A dot B dot C, which is equal to A dot B dot C. So what I did here, I made first bracket for the next two element and second bracket for the first two element, and I proved here that three elements is having same multiplication. Okay, so you may consider any counter example in order to prove this one. Okay, so it is similar like our first property too. So it is quite easy to prove Z under multiplication is a semi group. Okay, now last third one it is remaining. It is a distributive property, left and right distributive property. Now let's see our third property. So in our third property, we have to prove left and right distributive law. Okay, so take any three elements A dot B plus C, A dot B plus A dot C. Okay, this property hold easily. Just you may take any counter element here to prove this one. Okay, now and in second property A plus B dot C, A dot C plus B dot C, similar like our first property, you may easily verify this. Okay, it hold right and left distributive law. Okay, so these are the two distributive law. Just we have to apply here. Then if all these three properties hold, then we say that Z under addition and multiplication is a ring. Okay, so under addition multiplication it is always ring. So similarly we may prove rational number, real number, Q under addition with and multiplication, real number, Q under addition multiplication, C under addition multiplication, and Zn means group under modulo n under addition multiplication are a ring. Okay, so this is the homework for you all. Try to prove these are the ring. Okay, try to prove these examples. Okay, like Q plus R plus complex plus Zn plus, all are the ring. Need to satisfy only three properties, then we say that these are the ring. Okay, surely these are the ring. So this is for you all for homework. You may try. These are hold the all properties from ring. Okay, so similarly if we take the cross product for the two group or two uh, Q R complex Zn or Z. Okay, so if you take the cross product and if we apply all property for ring, it also shows that it hold the all properties from ring. Okay, so here you can see, if you want you may try for your homework remaining examples also. Okay, Z cross Z, Q cross Q, R cross R, C cross C, Zn cross Zn, Z cross Q, Q cross R, Q cross C, Q cross Z cross Q cross R. Okay, under addition and multiplication. Okay, all forms a ring. Okay, it satisfies all the properties of a ring and forms the ring. Okay, similarly matrix M n R. Okay, so we have n by n matrix M n R under addition, it is also a ring. Okay, so it is quite easy to prove this one. So you may try all these examples for your homework. These are so many of the examples, you may try it, and if you found anything difficult, let me know in a comment section. Okay, I will clear your doubts there. Okay, and if you found anything difficult, let me know. I will upload similar videos on my channel. Okay, so here one more property I wanted to explain here, MNR. Okay, that means matrix multiplication is abelian but not cyclic. Okay, MNR under addition is abelian group but not cyclic. Okay, and we know that abelian property never guarantee for a cyclic group. Okay, abelian group we cannot guarantee that it gives a cyclic group, but cyclic group always gives abelian group. Okay, these properties are coming from group theory that we need to know. Okay, before learning ring theory we need to understand properly group theory, then and only then ring theory is easier to understand. Okay, so I already uploaded videos on group theory too. Okay, so you may check into my playlist. I already uploaded plenty of the videos there. Okay, so I hope so you all have understood my today's lecture. uh, it is completely based on a ring theory. Okay, thank you everyone, thank you for my today's lecture.